talking about sampling from a population, but in our sampling, we are doing it using a proportion. All right, so yesterday or Monday, when we were here and I was telling you about the sample being the variable that changed. Remember how we kind of talked about average, we talked about IQ scores and how we all went out and we gathered up 10 IQ scores from people, right? We sampled 10 people and the average of our sample became the variable that changed, didn't it? X bar was the variable that changed. That's the variable that represents the mean, the average of our sample, the mean of our sample. Well, what we're talking about today is the proportion in a sample. So this is our last letter for P. This is the last use of the letter P for us for the semester, which no, it's not alive. We have a P value too. We got one more past this. All right. So we have P hat here, lowercase p hat. This represents the proportion. This is the same thing as a mean from a sample, right? This is the same thing as an average. This is our the proportion of successes, basically. All right. So P hat is found by taking the number of successes, lowercase x, the number of successes in a sample size. So if, for example, we were to find the number of people, let's say my question was about the number of people who had brown eyes, and I surveyed the class here. The number of successes would be the count, the value of you all who have brown eyes out of the entire class. And that proportion, right, that relative frequency, P hat would be a relative frequency basically. That would be the relative frequency of the number of people who had brown eyes in our classroom, right? P hat is the proportion, it's a statistic that represents, or it's a statistic that, that describes our sample. Now, most of the time we are given P hat. Again, it represents that statistic. It's a decimal value that usually we are given. There are times, however, where you may be asked to go back and calculate P hat, or possibly if you know P hat and you know the sample size, we might actually have to do some algebra here in a math class, and you might have to go back and figure out what X is. You think you can do that? You know what P hat is and you know what the sample size is, can you work backwards using algebra and figure out what X is? Okay, if not, ask me and we'll talk about it. Now, for our sampling distribution, so those are the values up there. Those are the definitions that you want to make sure that you have written down. When we talk about our description, this time of a proportion. Remember how we talked about shape, center, and spread last time? Okay, well, we still talk about that here. The shape of our sampling distribution is approximately normal. And I'm going to back up for a second. What was the value, what was the numerical value that we said for a sample size on a mean that guaranteed us, it invoked the central limit theorem, it guaranteed us that we didn't care what the population shape was. We knew that our sample was going to be normal if the sample size was what? Was it less than 30? Larger than or equal to 30. Greater than or equal to 30. All right. So on a mean, that's our central limit theorem evoker right there. That's the guy. That's the number. In a proportion, right? We still have to have something similar, but that's what NP times 1 minus P has to do with, all right? It's still the same concept. If you check that your sample size, your proportion of successes times the proportion of basically failures is greater than or equal to 10, then you have the same concept that we are going to end up with a normally distributed sample size. Now, I'm not going to go through the same applet that we did the other day. Remember how we started out and we were kind of playing around with sample sizes and everything to see how in fact it does change? You can do that if you want under that same applet portion, that same applet part of StatCrunch, but that's what the shape is telling us there. The center of our sampling, of our sample proportion, right? The center of our sample proportion, in other words, the mean of our sampling distribution, mu sub p hat, is going to be the same as the population's proportion, right? The mean of the sample is the same as the mean of the population. We're just describing it using p's now instead of x bars, okay? So the mean of the sample proportion is equal to the mean of the population's proportion. And remember that standard deviation was the component that changed, right? Each time I changed the sample size, the standard deviation changed on my sampling distributions, didn't it? Do you all remember that from the other day, right? We kept saying that the middle, the average, the mean of our IQ scores all kept staying around 100, but the standard deviation kept changing as we increased our sample size. That's why the standard deviation here is going to change, right? It's the same concept. We just have a different formula to find it. It says that the standard deviation of the sample proportion, sigma p hat, is equal to all of that stuff underneath the square root symbol, all right? Most people don't have a problem with that. It's just order of operations, putting it into your calculator in the right way, okay? And then finally, who remembers how many criteria were there, since you just took a test over, how many criteria were there that you had to check off for a distribution to be binomial? 4, right? There was 4 criteria that had to be met in order for a distribution to be binomial. One of those criteria was that it had to be independent, right? It had to be independent. We'll notice that we want to check for independence here. And this is a numerical way for us to do it. 99% of the time, we don't have to calculate this, but this is the calculation should you want to. You're trying to make sure that your sample purport, or that your sample is less than 5% of the population. Okay. You can't do that calculation if you don't know what the size of your population is. So sometimes that doesn't even work, right? But in essence, that's what you're calculating should you need to, all right? So you can quantifiably, with a numerical number, calculate whether or not it's independent. Most of the time we just say people were independent, right? People are independent as far as our, if that's what we were looking at. Okay, do we have an idea? Have I given you enough time to make sure that you have these things written down as well? Okay, all of those formulas are going to be very important for us. So I gave you this problem on your paper so that we can kind of walk through and highlight and circle and write down certain aspects of it. So this is the example that's on your paper above. It says a quality control director of a small company that manufactures exercise equipment knows that 10% of their products are defective. Market research shows that only 30% of the customers will use the product in the first year after the sale. So the manufacturer expects that 3% of the units will be returned for service under a 1-year full warranty. The company expects to sell 600 units next year. There is an awful lot of extraneous information in this paragraph, all right? There's an awful lot of things that we don't really need to know about, okay? So let's go through and kind of look at what we have here. It says quality controls knows that 10% of their products are defective, blah, blah, blah. Okay, let's look at the first bullet down there. It says describe the sampling distribution of p hat for the proportion of 600 units that will be returned for service. I want you to highlight, underline, circle, whatever you want to do, but we're looking at the proportion of units that will be returned for service. That helps us identify when we go back up into this paragraph, somebody look and find where we're referring to the number of units or the proportion of units that will be returned for service. Right, 3%. So all of the other information above that is actually disregarded. We needed to read down to where we read through the question first and then look to what is the question actually asking? What am I ultimately looking for? Then go back and kind of pick those types of things out. Okay, now is always a good time to go ahead and once we understand what the, now that we understand what the question is being asked, let's identify all the variables. Let's start assigning variables and see what we've got here, okay? So we know that what is 3% actually? What variable do you suppose I would assign to 3%? Yeah, let me ask a better question. Let me ask that a different way. Is 3% a parameter? Is it talking about a population, or is 3% referring to a sample? Read it again. Again. Manufacturers expect that 3% of the units will be returned for service under a 1-year full warranty. The company expects to sell 600 units next year. 3% is talking about the population, isn't it? They don't have a value yet for the 600 units that they've sold. They know that on average, right, they expect 3% of what they sell to be defective or something like that, out of warranty, something will be returned. So 3% is about the population, okay? So I'm going to write that down. The symbol for the population is P. That's a proportion. That's little p. Little p is 0.03. That's about the population. Now, what's the sample size that we are referring to? Okay, so N is equal to 600. And at this point, when it says describe the sampling distribution, we are asked to verify. This is where we start identifying and verifying shape, center, and spread. Okay. We are going to verify the shape. All right. We are not told in anywhere, any shape or form in here whether or not this comes from a normal distribution or anything like that, are we? We just know, we don't know any information about that. But we were just told that in the problem, I mean, in your formulas you wrote down, that if I were to multiply the sample size times the proportion times 1 minus the proportion, if that's greater than or equal to 10, I don't care what the population shape is because my sample will be normally distributed. So for this case, we're going to multiply 600 times 0.03 times 0.97. Is that greater than or equal to 10? Somebody tell me to 2 decimal places what that value is.
17.46.
All right. 17.46 is obviously greater than or equal to 10. So we can say that the shape is normal. Okay, we can say that the shape is normal. Do we understand why that's the case? Because we defined it that way above, right? We defined it that way from above. Right? Any questions on this before I move on?
How'd you know to multiply 0.97?
I did the subtraction already, so it's 1 minus 0.03, which is 0.97. Okay. Just following, just plugging it into that formula that we had. That's the shape. The center, remember the center is always talking about the mean. So the center said that the mean of P hat has to be equal to the population P, or in other words, 0.03, right? The mean of the sample is the same as the mean of the population, just like in class the other day. And the spread has to do with the standard deviation of our sample proportion. Now I want everybody to get out the calculator that you think you're going to be using. We're going to work on this. We have the square root of P times 1 minus P all over N. So in other words, we have 0.03 in the numerator times 0.97 divided by 600. Then take the square root. What I'm looking for is that number right there, all right, 0.006964. Okay, did everybody get that? Check and make sure when you put it into your calculator that you can actually get that value. Okay? Did everybody get this? Shake your head yes or no. Still working on it? So we have found the shape. Okay, shape, center, and spread. If you don't have that down, write that number down right there. All right, so we have verified that this is that the sample that I pull, right? If I wanted to know what is the probability that in a sample of 600, I have 3% of them that are defective or something like that, right? What we're looking at is in my sampling, I know that because NP 1 minus P is greater than 10, that this behaves in a normal way, which means we can go use the normal calculator, all right? We're going to use the normal calculator on this. So these questions here that we have, which say, I have 3 different questions down here. The first one says, what's the probability that more than 3% of the 600 units will be returned for service? What's the probability that I get a sample proportion, P hat, greater than 0.03? Okay? That's what we're looking at. So we go to StatCrunch. We have to be logged into StatCrunch, so we're going to go to the normal calculator of StatCrunch. And when we get to the normal calculator, we use it the same way we've been using it in chapter 7, 8.1, and now 8.2. Calculator is still the same. The input that we're going to be using is a little bit different. The mean that we're using is the mean of our sample, which is the same as the mean of the population, right? Okay, which should be 0.03. The standard deviation was the standard deviation of the sample means, which we did our calculation for, and we found that that was 0.006964. The question is, what is the likelihood, what's the probability that I get a sample proportion greater than 0.03? I know, it's kind of a crazy question, right? It's a 50-50 chance that you get a sample proportion greater than 0.03. 0.03 was our number we were using as this anyway, right? If 0.03 is the sample mean, if 0.03 is the mean of the population and 0.03 is the mean of my sample mean, we are assuming that if 0.03 then is the middle, then of course you would have 50% more and 50% less, right? Because it's the middle, right? All right, it's kind of a silly question, but there you go. You might have that. That's how come this came out to be 50, right? 0.03 is the center, so you would have 50% greater or 50% less. Now the next question says, what's the probability that more than 5%, what's the probability, I'm thinking 5%, what's the probability that I have a proportion out of 600 units that are returned, and that proportion is 0.05. So in other words, what's the likelihood that I get 5% of a 600 unit lot returned? So all I have to do is come back and change from 0.03 to 0.05. Now what do we get? 0.002? Yeah, 0.002? Okay. So in other words, we are less than 1%, right? It's unusual. It would be unusual, wouldn't it, to have more than 5% out of 600 units returned for service, wouldn't it? Yeah? Because this is less than 1%, isn't it? 0.002 is less than 1%. This would be unusual to have happen. If you're thinking quality control, this is kind of the things that you want to be thinking about, right? How can I use statistics to help me in a business sense? Would it be unusual, and I just answered that last question, would it be unusual to have 600 units with 5% of them returned? Yes, it would, because this is obviously less than 5%, right? So yes, it would be unusual. Okay. So is this really any different from what we were doing last time? It's exactly the same thing, isn't it? It's kind of rehashing it. So if you didn't understand it last time, maybe it'll be a little bit better this time, right? Okay. So what I'm going to give you a chance to do is I want you to work the rest of those problems. So 1, 2, and 3 you have right there on your paper, all right? On the back of, or on the continuation of your paper, and see if you can apply this new concept of a sample proportion to these questions here. The only thing that has changed is your shape, your center, and your spread. All right, that's the only thing that changed. We're going to take just a little time to be able to finish that.